I have simplified Chapter 7. Chapter 7 deals with ionic bonds and ionic compounds. I'm just going to hit the high points on ionic compounds. An ionic bond is formed when a cation, which is positive, attracts to a negative ion, the anion. So for example, metals tend to be positive. Metals tend to form your cations. So like sodium would be positive, and it's actually a positive one charge. When there's an attraction between a positive and a negative, that forms an ionic bond. Metals are positive. Non-metals like chlorine tend to form negative ions. When you form ionic compounds, they have to be neutral, so the charges must balance out. The charges are not always 1-to-1 or 2-to-2, so I will show you how to balance those charges out a little bit later. Properties of these ionic compounds, these metal, non-metal compounds. And when I think of ionic compounds, the most familiar one to you is table salt, NaCl. They tend to have a high melting point, so they're going to be solids at room temperature because they have a high melting point. They also tend to be crystals if you actually look at the structure. If you were to look at the structure atomically, molecularly, they would be crystalline. These will dissolve in water. So when I put sodium and chloride in water, salt in water, it will break apart into sodium ions and chloride ions. And they also conduct electricity. Whenever we form compounds, whether they're ionic or we're going to talk about covalent later, we follow the octet rule. And the octet rule says that elements want to gain, lose, or share electrons in order to acquire the electron configuration of noble gases. Noble gases have 8 valence electrons. They're very stable. Well, other elements want to be like the noble gases and get those 8 valence electrons. Now, when we talk about ionic bonds, that's gaining or losing electrons. Sharing electrons, that would be covalent bonding. But in either case, elements want to get 8 valence electrons. And the exceptions are hydrogen and helium. They only have 2 valence electrons because they're in the first row of the periodic table. So when we form chemical bonds, again, whether that's ionic or covalent, but we're just looking at ionic right here, they focus on the atom's valence electrons, the outer shell electrons. And we're going to draw what are called Lewis dot diagrams. So let me give you an example. Lithium's Lewis dot diagram would look like this. Lithium is in group 1A. So that means it has 1 valence electron. So the Lewis dot diagram for lithium looks like this. Just got 1 dot. 1 valence electron. I'll make an X there for the valence electron. Carbon. Carbon is in group 4A. So that means it has 4 valence electrons. 1, 2, 3, 4. And I'm using X's. You can use dots. You can use whatever symbols you want to. Let's do a transition metal. Transition metal like scandium, if you look on your periodic table. Scandium is a transition metal. It's in the B groups. The B groups have 2 valence electrons. Phosphorus. Phosphorus has, it's in group 5A, so phosphorus has 5 valence electrons. So you just put 5 dots. First 4 go our separate sides, and then the 5th one you can pair up anywhere. But that would have 5. The most you can have would be the noble gases, like neon. Neon has 8. So the most you can have, the most valence electrons you could have, are 8. And again, I'm just looking at the group number, group 1A, 2A, 3A, whatever. And if you're in the B groups, you have 2, like scandium. So that's a Lewis dot diagram. Binary ionic compounds consist of only 2 elements. And we're going to denote those ratios using the empirical formula. So we're going to put these together. So let's say I want to put sodium with oxygen. Sodium with oxygen. And I want to know what the empirical formula is for sodium with oxygen. Well, here's how I do it. Sodium has, you find it on the periodic table, it's in group 1A, so it has 1 dot. Oxygen is in group 6A, so it has 6 dots. And again, I'm going to have to use X's because the dots aren't showing up on here. Sodium is a metal. Metals tend to lose electrons. So sodium is going to donate its electron to oxygen. But oxygen only has 6. Oxygen wants 8. So I need another sodium. That sodium donates its electron to oxygen. Oxygen now has 8, so it's happy. Sodium has the electron configuration of neon because sodium has lost one valence electron. And if you look at your periodic table, if sodium loses one, it has the same configuration as neon. So it's happy as well. So sodium's happy, it's got 8 valence. Oxygen's happy, it's got 8 valence. The empirical formula for this would be 2 sodium for every 1 oxygen. So this is my empirical formula. So metals tend to lose electrons. Nonmetals tend to gain electrons. And that's always the case. Let me go through one more example. We're going to put these two together, and I want to know the empirical formula. Well, the first thing is find out how many valence electrons you have. Magnesium has 2. It's in group 2A. Phosphorus is in group 5A. So it's got 5. Okay, metals lose. So magnesium loses both of its electrons. Okay, so magnesium's happy. It lost both of its electrons. Magnesium now has the same electron configuration as neon because it's lost 2. So it's happy. P only has 7 now. It needs 8. So I need another metal. I need another magnesium. So this magnesium is going to donate 1 there. Now the P is happy. So this Mg is happy. This P is happy. This magnesium, the third one, still has an electron left, so I need another phosphorus. And you kind of see how this goes. You keep adding these until everything has 8 valence electrons. Now this magnesium's okay because it's lost 2. It's got the same configuration as neon. P's not happy, so I need another magnesium. And eventually, after the metals lose their electrons and the nonmetals gain their electrons to get 8, so everything's got 8, it will work itself out. And it will give me the empirical formula. In this case, the empirical formula shows me that there are 3 magnesium, so it would be Mg3, and 2 phosphorus. Mg3, P2. That's my empirical formula. So, ionic compounds form because of this. Magnesium becomes positive. It loses 2 valence electrons. Phosphorus gains 3 electrons and becomes negative. And an ionic bond is formed because positive attracts negative. Magnesium's positive, it attracts negative phosphorus. There's your ionic bond. And this is my empirical formula, the reduced form for this compound.